Okay, so yesterday we were looking at the idea of resource sharing, and in particular the approach that we are taking in order to implement resource sharing is a technique that is sometimes referred to as folding. Right? The idea being that you have a set of operations that need to be completed and you have a finite set of hardware resources. You are going to fold multiple operations onto the same hardware resource so that the hardware resource can be time multiplexed, and over a certain number of clock cycles will finish all the iterations required and all the operations required to complete one iteration. Okay, so what we are going to do today is to look at a couple of more examples of folding, or rather go a little bit deeper into how the folding can be implemented in practice. Okay, so to start with, what I'm going to do is once again just review the example that we took up yesterday, which is just adding three streams together. Okay, so A, B and C are three streams of data, meaning that they are sampled sequences of data. I want to add all of them together, first A and B, and then add that result to C and generate Y of n. Okay, now to implement folding, we are going to focus only on what are the actual functional operations that need to be implemented. So in other words, when I draw the data flow graph corresponding to this, I'm not going to worry about the sources. I'm not going to draw a node to indicate that there is a source over here and that some data is coming from this source, because from a functional point of view there is no hardware unit associated with that. Okay, so if I draw the equivalent data flow graph, essentially it will just look like this. There is one addition and there is another addition. Okay, I'm not even going to draw the incoming edges because those are essentially just coming from sources, from external sources. There are no other dependencies as such. So for all practical purposes, I can just assume that the addition A1 can execute at any point in time because the A of n and B of n values are already going to be present. The only restriction that I really have as far as this data flow graph is concerned is A2 can execute only after A1 for a given iteration. So that is pretty much all the information that is being captured by this data flow graph. Okay. Now let's take this data flow graph. The hardware that I have available is an adder pipelined to depth 1. Which essentially is something that looks like this. There is an adder and a register at the output. It takes two inputs and it generates one output. This is what I'm assuming is the hardware unit available to me. Only one type of hardware. Okay, and since I have already assumed that there is a register at the output, I'm not really going to bother with talking about a critical path as such. I'm just going to say basically that this adder has a latency of 1 clock cycle and an initiation interval of 1 clock cycle. Okay. And what is the duration of that clock cycle? How many nanoseconds or how many picoseconds? I don't really care. I'm not mentioning that at the moment because my assumption is that I'm going to use this in a clocked system where that clock will be sufficiently long period so that there is no violation of timing over here. Okay. So with this assumption, what I'm going to do is, now if I want to create an equivalent hardware representation for this, I need to first choose my folding factor n. Okay, so let's start with a folding factor of n equal to 2, right? What that effectively means is that the time instance or the scheduling instance right, the times at which the two operations A1 and A2 are scheduled must fall within the values 0 and 1. Okay, in other words, n equal to 2 essentially means that I'm alternating 0, 1, 0, 1, 0, 1, right? Those are the two phases of operation. Okay. So any of the operations A1 and A2 need to get scheduled in either time 0 or in time 1. Okay. And also, as we discussed yesterday, from just observing this data flow graph, we can pretty much see that A2 has to happen after A1, right? And in fact, one cycle after A1. From that, what we can see is the only possible choices, only valid choices are that T of A1 is equal to 0 and T of A2 is equal to 1, where T of a node is the time instant at which it is scheduled. Okay, these are the only choices which allow us to satisfy the constraints under this particular implementation. Okay, so now let's go further with that, and how do we translate this into a complete hardware architecture? Okay, once I have these two numbers, what I can say is, let's look at the link from A1 to A2, right? A1 is now scheduled at time 0, A2 is scheduled at time 1. A1 is scheduled at time 0, meaning that the output of A1 will be ready at time 1, because my hardware is such that after I give the inputs, it adds and then puts it into a register, and the output actually is available only on the next clock cycle. Okay. So for this edge A1 to A2, what I essentially end up having is A1 scheduled at 0, output is ready at 1, okay, and A2 is scheduled at 1. Okay, so what I'm going to do is define a term over here saying that df, right? The idea of df is simply, are there any extra delays or registers required on the edge connecting A1 to A2? Okay, and in this case the df from A1 to A2 I define as the time when A2 is scheduled minus the time when A1 finishes right, where this PA is the pipeline latency of an adder, which is equal to 1 time unit, right? And in addition, I'm going to say that if there were edges, or rather if there were actual delay tokens present on the edge between A1 to A2, then it gives me extra time. In other words, A2 is now dependent on one iteration earlier or two iterations earlier, or in general W iterations earlier output produced by A1, right? If A1 produces its first output at T of A1 plus PA, it would have produced the previous output at T of A1 plus PA minus N. Okay. Right. So let's take a moment to understand exactly what this equation is saying. I have defined one term df. Okay. And over here what I am saying is the value of that df is the time when A2 is scheduled minus the time when A1 finishes. Okay. So if that number is not equal to 0, what it means is after A1 has finished, I need to take the data output from A1 and save it somewhere. I need to store it in some registers until A2 is ready to use it. Okay. If that number is negative, there is a serious problem. That's not acceptable. Okay. It basically means that I'm violating a constraint. The additional thing that I have over here is just this second part, which basically says if there were token delays present on the A1 A2 edge, meaning that A2 depends on one iteration previous sample of A1, then I actually get some extra freedom. I can add W times N or 1 times N to this DF value. Effectively what it's saying is, look, I computed the value of A1 in one previous iteration. I then just store it for N extra cycles and you then use it for A2. The interesting thing is, what this allows you to do is T of A2 can now be less than T of A1, right? If this W is greater than 0, in other words, I don't care if this T of A2 minus T of A1 plus PA is negative, because the W might be sufficient to bring it positive. Okay, let's walk through this example, complete it. In this particular case, what I have is that DF from A1 to A2 is T of A2 is 1, T of A1 is 0 plus PA is equal to 1, and the W in this case is 0 times N. Okay, which means that DF is equal to 0. Right? Translate that into equivalent hardware. My hardware now looks like this. I have an adder. This is my pipelined adder unit. Okay. All that I am saying over here effectively is the two inputs over here, rather than drawing multiplexers, I am going to use a slightly different notation. I'll use some kind of switches to basically indicate that these are switches that are sort of rotating across different phases, 0, 1, 0, 1, 0, 1 and so on, right? A multiplexer is how it is finally going to get implemented, but visually sometimes it is all another way of looking at it is to think of it as rotating switches where you are just going through different phases cyclically. Okay, so for that what we say is there is a phase 0 and a phase 1. Similarly, there is a phase 0 and a phase 1. Okay, now according to this schedule that I have got over here, A1 addition occurs at time 0, which basically means that how do I get that to happen? I make sure that A of N and B of N are given as the two inputs to the adder at time 0. Okay, A of 2 occurs at time 1, which means that I need to make sure that C of N and the output of the adder with 0 extra delay elements associated with it needs to be fed back over here at time 1. Okay, so this is where that DF comes into the picture. In this case, DF is equal to 0, so there are no extra registers required on this edge. Right? To make this a little bit clearer, let's take the same example but work through it under the situation where N is equal to 3, which means that the T values must be in the range 0, 1 or 2. Okay, and over here arbitrarily I am going to assume T of A1 is equal to 0 and T of A2 is equal to 2. What are the possible choices? T of A1 equal to 0, T of A2 equal to 1 would also be valid. A1 equal to 1, A2 equal to 2 would be valid, right? But A1 equal to 0, A2 equal to 0 is still not going to be valid. A1 equal to 1, A2 equal to 0 or 1 is not valid, for example, right? Or at least as things stand over here, they are not; those are not valid implementations, right? So with this, what do we get? The DF value now becomes the time of A2 minus the end of A1 right, plus W into N, okay, which in this case is 2 minus 0 plus 1 plus 0, or in other words it's equal to 1. Okay, and if I want to draw the equivalent hardware architecture, it essentially says it will look like this adder. Right? So now there are three choices out here. Okay, and I now need to decide what happens at each time. T of A1 is 0. So A of n and B of n need to be made available as inputs to the adder at time 0. Okay, there is no operation at time 1. Therefore, there are no inputs to be given to the adder at that time. And at time 2, what I have is C of n to be provided here, and this output of the adder to be provided, but now because df was equal to 1, I need to delay it further by 1 register. Okay, and if you work through the steps, time instance 0, 1, 2, 3, 4, 5, 6, and compute the phase of the clock, right? So the phase of the clock is essentially what I'm referring to over here, right? It is either in phase 0 or phase 1 or phase 2, then goes back to 0, 1, 2, 0, 1, 2, 0, 1, 2 cyclically, right? So depending on the phase of the clock, I will essentially get different inputs being applied to the inputs, or different values being applied to the inputs of the adder. Okay, and each of them correspondingly are implementing one of the operations in the data flow graph. Okay, so that is where this df essentially becomes useful. All that it tells us is we can automate this process of figuring out how many registers to put when we are taking a particular output and connecting it to the appropriate input. Okay, just to round this off, we'll take one further example, right, before going on to a more complex example which will be useful finally. I'm going to take the same A1, A2, but now I'm going to say I'm pipelining this, right, put a delay element on it. Okay, so this basically says that W is equal to 1. Okay, now again let's go back to, or let's just continue working with n equal to 3. Okay, now interestingly I can choose any other value of T of A1, and just to sort of see how to do things, I'm going to choose T of A1 equal to 1, T of A2 equal to 0. Okay, and let's see what happens to the df value now. Df equals T of A2 minus T of A1 plus PA plus W times n. This is equal to 0 minus 1 plus 1. Normally this would not have been acceptable, plus 1 into 3. The fact that there was that sample delay, one iteration delay, basically means that now the df has become positive, right? So it's 0 minus 2 plus 3 equal to plus 1. Okay, what does my hardware architecture look like? I have an adder, okay, Now I know that T of A1 is equal to 1, which means that I can straight away say from there A of n and B of n must be fed to the 1 inputs of the corresponding switches or multiplexers. Okay, and what about T of A2? It is 0, right? So in other words, the A2 operation is going to happen during phase 0. C of n can be applied over here, and this output can be fed in, but there is a df equal to 1. Okay, and if you work through the time steps corresponding to this, the main thing that you need to note over here is because of this sample delay, right, the output produced by A0 is something that would have been consumed by A1 of 0 would have been consumed normally by A2 of minus 1. So A1 of 1 is what is going to be required by A2 of 0. Okay, sorry, the other way around, right? So A2 of 0 is going to use something that was generated one iteration earlier, A1 of minus 1. A2 of 1 will be using A1 of 0. A2 of 2 will be using A1 of 1, and so on. Okay, so if we write out the time sequence saying these are the time instants at which the different A of n, B of n, C of n values are being generated and applied over here, right, correspondingly everything will change. Of course, you need to keep one thing in mind. I arbitrarily did one pipelining step over here. That is to say, I inserted one iteration delay between A1 and A2. Okay, but keep in mind that if I am actually doing pipelining, what do I need to do? I need to make sure that since my original graph looked like this, right, if I am actually doing a pipelining, I need to keep in mind that in principle, even though I am not marking them, these are also nodes as far as the system is concerned, which means that a proper pipelining will have to be like this. Okay, if I insert a delay element over here, I also need to insert one delay here so that the C gets delayed appropriately by one clock cycle before it's being applied to the input. Okay, when I draw the data flow graph, that detail gets hidden away because I am not treating my sources as separate nodes, right? So in other words, these kind of things, when you are actually implementing them, you need to apply your mind and make sure that you are doing it correctly. The pipelining step that you use is valid and that you have delayed all the inputs appropriately so that you get the correct output. As long as you take care of that, the approach itself will work. Okay. Alright, so now what we are going to do is take up a somewhat more complex example, right, and work through that as well, just to sort of get practice in the idea of how to implement folded architectures, right. One thing to keep in mind, in practice it is very unlikely that you will be manually doing this kind of folding. You are not going to individually decide what is going to go into each step. But the point of this course is for you to understand the principles involved. What does it mean to have different operations scheduled at different time steps, right? And when a tool or a compiler says that it is putting different operations in different time steps or different control steps, what is the implication? What does it mean? How is it going to do it? Okay, if you were to do it by hand, how could you actually build such a system? That knowledge is the important part. Okay, so the larger example that we are going to take is something called a biquad filter structure, right? This is a somewhat common occurrence in signal processing. It is essentially a second order filter structure. It has both FIR and IIR portions, right? And it has a number of useful mathematical properties. Primarily from the point of view of the implementation, it turns out that this is a fairly robust and stable to a lot of different noise effects. Okay, so it's very popular in practice. It is used a lot. But as far as we are concerned, we are using it as a slightly more complex example of a signal processing system that needs to be implemented. So what I'm going to draw is a data flow graph corresponding to one particular realization of this filter. We'll look at all the different operations that need to be implemented. Then say if I have a finite set of resources, how do I go about folding everything onto this and getting it working? Okay. So the backward filter itself looks like this. Okay, so what you can see over here is there are 4 addition operations and 4 multiplications. Okay, the structure itself, overall you can sort of see what is happening out here, right? It has these 2 feedback loops, right? But the rest of it is essentially going in a feed forward manner. Right? So like I said, there are both FIR as well as IIR components to this structure, right? It's essentially a second order structure because up to y of n minus 2 and x of n minus 2 are being used in the computations that we have over here. Okay. Now later on we will actually see what the original structure looks like. This is already a structure that has been slightly retimed and pipelined to make it possible to do a scheduling. Right? The original structure actually looks a bit cleaner than this, but it doesn't matter. As far as we are concerned, we are just going to use this as our starting point. Okay. So what I'm going to do now is basically associate labels with each of these operations, but more importantly what I'm going to do is define something called a folding set. Okay. In order to understand a folding set, it might be easier if we just go back to our original examples. What I'm going to say over here is, if I do this, right, that is t of a1 equal to 0, t of a2 equal to 1, I can also equivalently write that by saying that there is a folding set which has the elements a1 and a2. This is the folding set for the adder. Okay. The meaning of this notation is basically that the adder has 2 phases in which it can operate, and because I have given this a1 comma a2, it means that a1 is going to execute in phase 0 and a2 is going to execute in phase 1. Okay. Even though I am using curly brackets, it is not unordered set. The order is important over here, a1 followed by a2. So in the next example, in this one over here, effectively what this corresponds to is the folding set is s equal to a1. What happens in the time instant 1? Nothing. So I'll just put a null over there, right? Use the symbol phi to indicate a null element, and a2. right? Either a null or just a dash, essentially to indicate that no operation is happening over there. Okay, and similarly for this third example, what I would have is this corresponds to S is equal to A2 at time 0, A1 at time 1, and nothing at time 2. Right? And using the same notation, what I end up with is further, and before I give that notation, I'm going to make the assumption that the adder is pipelined to depth 1, multiplier pipelined to depth 2, right? This is what we discussed yesterday. I'm just repeating the same assumptions that we had yesterday. All that this means is, like I said yesterday, the multiplier, I can give it inputs on every clock cycle, but it has a latency of 2 cycles, so the output becomes ready only after 2 cycles. Okay? Another way of writing it is PM is equal to 2 in this case. Okay? In terms of the notation that we were talking about earlier, the PM for the multiplier is equal to 2. Okay? We will see how that applies when we are basically doing the DF computations. So now with this information in place, I'm going to write down S1, which is for the adder, right? I'm going to assume I have one adder and one multiplier, right? And before I can write S, I also need to know what value of N to use. What's a suitable value of N? How many phases do I need? 4. Why 4? Because there are 4 adders. So with one piece of hardware, I could do it in 4 clock cycles. How exactly, I don't know yet, but that's the bare minimum, that much I can be sure of. Similarly, 4 multiplication operations, I can finish those within 4 clock cycles, 4 phases. So I will start off with the assumption that N is equal to 4. If it turns out that it's not going to work, I'll probably have to change it and use a larger value of N. Okay? With that choice, N is equal to 4, what I have is, I have the ability to schedule 4 different units across 4 phases of time. Okay? I'm going to call the operations themselves as, I'll just label all of them. This is A1, A2, A3, A4, M1, M2, M3, M4. Okay, so the set S1 for the adder, I'm just going to give you this information, right? Is basically going to be A2, A3, A1 and A4. Okay. In other words, another way of writing this would be to say that A1 is scheduled at time 2, A2 is scheduled at time 0, A3 is scheduled at time 1 and A4 is scheduled at time 3. Okay, so both the notations that I have given here, where I put that bar and I put a number after it, as well as this set notation that I have, or the list notation that I have given over here, both are conveying the same information. Okay, S2, which is for the multiplier, is M1, then M4, M2 and then M3. Okay, which is equivalent to saying M1 happens at time 0, M2 happens at time 2, M3 happens at time 3, and M4 happens at time 1. Okay. How did I come up with this ordering? We'll get to that later. Okay. That essentially is the problem. I mean, that ultimately is the most interesting problem in this entire thing, right? How do I come up with a valid set of these assignments so that none of the constraints are violated, and at the same time I am able to execute all my operations with a limited amount of hardware, in this case with one adder and one multiplier, right? So if I wanted to systematically take any data flow graph and implement it on a limited amount of hardware, effectively this is what needs to be done. I need to somehow come up with these assignments. How we come up with the assignments is the topic of scheduling. Okay, we'll get to that next after we have completed this. The purpose of doing this exercise is to say, okay, once I have a schedule, how do I, at least this is one way by which I can implement it in hardware. Okay. Alright, so with this information that I have over here, let's see if we can go forward and compute all the DF values. Okay. So in order to talk about the DF values, we need to sort of understand what are the different edges that are present in this data flow graph to start with, right? What I mean by that is, even though because what I have drawn over here is not really a data flow graph, it is a block diagram, right? So there are, for example, these junction points over here where something splits off into two, or when multiple mergers of course are indicated by additions, but the splitting off of into two, right, as far as the block diagram is concerned, is a clean way of drawing it. But as far as the data flow graph is concerned, that's actually hiding some information, because these points that I have over here, those junction points, are not really separate nodes in the data flow graph. So if I look at what are all the edges that are present in the DFG, I find, for example, that I have an edge which is going from A1 to M2, right? Another edge is going from A1 to A2, and the edge from A1 to A2 has one delay element on it. The edge from A1 to M2 also has one delay element on it. The edge from A1 to M4 has two delay elements on it, because when I take that path, I have to pass through two such registers, two delay elements. Okay, so there are two options available to you here. Either you just go through this and make sure that you count the number of delay elements properly, or you redraw the original block diagram as a data flow graph just for clarity, so that the exact number of delay elements are easily visible. Okay. So obviously there are more edges, right? I'm not going to draw every single one of them over here. You can do that quite easily on your own. So what I'm going to do instead is try and calculate the DF values, right? So let's look at, for example, the DF value between edge A1 to A2, right? How would I compute it? I need the schedule time of A2, which in this case is 0, minus the finishing time of A1. A1 is an adder. It's scheduled at time 2. It has a pipeline latency of 1. Okay. So this is what I have. This is T of A2 minus finishing time of A1. So far it doesn't look good. It's looking negative, but I have one delay element. So plus 1 into 4. So DF over here becomes equal to 1. Okay. Let's look at DF from A1 to M2. In this case, once again, the schedule time of M2 is 2. The finishing time of A1 is 2 plus 1 equal to 3. Okay. Again, it would have been negative except for the fact that there is one delay over here. So what I get is 4 plus 2, 6 minus 3 is equal to 3. Right? What about the DF from A1 to M4? In this case it is 1 minus 3 plus 2 into 4. Okay, so 1 minus 3 minus 2 plus 8 is equal to 6. Right? Similarly, I can go ahead and calculate all the M values. One particular example I am just going to take because it also brings out, for example, the fact that we are using a multiplier is from M2 to A4. Okay, so the DF that I would have from M2 to A4 would be equal to, what time is A4 scheduled? It is at 3. What time does M2 complete? It is scheduled at 2 and it has a pipeline latency of 2. Okay, so 3 minus 4 plus 1 into 4. Right? So basically it becomes 4 minus 1 is equal to 3. Right? And in this way, one thing that you can see over here is, for example, just to sort of simplify this, or rather one example over here is where W is equal to 0, right? So the A3 to A1 edge, DF from A3 to A1, when is A1 scheduled? A1 is scheduled at time 2 minus A3 is scheduled at time 1, and it has a pipeline latency of 1 because it's an adder, plus 0 into 4. This is an example where it is 0. Okay, so in other words, all that we really need to do is work through every single edge in this graph and make sure that the resulting DF values are non-negative. They can be 0 or some positive value. Okay, as long as they are 0 or some positive value, it means that this set of schedule instants that I chose, right, or the folding sets that I chose are valid. There is no violation over here. Okay, what does the hardware architecture corresponding to this look like? It would be, I have one adder, and one multiplier. Right? Like I said, I'm basically drawing two registers after the multiplier to indicate that it is pipelined to a depth of 2. I don't really need to do that. How it is implemented internally, I don't really care. Okay. Now the thing over here is there are 4 different options, right? Right? And once I have this architecture in place, all that I need to do is find out at phase 0 what is supposed to be computed on the adder. Let's go look at our schedule. At phase 0, A2 is going to be computed on the adder. Okay? Where are the inputs to A2 coming from? They are both coming from the adder itself. Okay? Because the inputs to A2 are, one is from A1 and the other is from A4. Right? In other words, both are some outputs that were generated by the adder at some previous instance of time. Okay, so just for understanding, let's put down this over here. This is corresponds to W equal to 0, and the DF value on A4 to A2 is in this case 0 minus sorry, I think I have got these numbers a little bit wrong. This should actually have been, so in other words, actually this is a problem, right? As you can see over here, if I actually had these values, it means that there is a problem over here, right? So what I have is 0 minus 3 plus 1. This is definitely not acceptable. Okay? So it turns out that the numbers I had put down over here, I think I had actually made an error over here inadvertently. Okay, I'll correct it and I'll put the updated thing. We'll go over that once again briefly in the next class if necessary. But let me just correct it for now. This should actually be, this should be 0. This should be 1, 3 and 2. Okay. It doesn't really change any of the other computations too much, so don't worry about it. You can actually just go through and calculate and verify the rest of the values. Some of these DF numbers of course will change. You need to recompute them because the A1, A2, all of these values have now changed, right? The M values don't change, but the A values, because I have updated them, you will need to recompute them. Okay. So once I have this updated value anyway, what would happen is, with this, what I would get on DF from A4 to A2 would be 1 minus 0 plus 1 plus 0. So DF would be equal to 0. Okay. And the DF over here would be from A1 to A2 would be equal to 1 minus 3 plus 1 plus 1 into 4, or in other words is equal to 1. Okay. For now, these are the only two numbers that I care about, so that I can at least tell you what happens at, well, time instant 1. Okay, I need to correct this. Right? If I have this structure, then essentially what I'm going to say is, going down to my next diagram, at time instant 1, what are the two inputs that I should have coming into my adder? Right? I'm going to say that the top one corresponds to the output from A1 and the bottom one corresponds to A4. I'm just arbitrarily making that choice. Okay. Where does that actually physically come from? The output A1 to A2 is the output of the adder, but with one extra delay on it. Whereas A4 is the output of the same adder, but with DF equal to 0. Okay, so now you can see how you would go about constructing the entire structure, right? What I'm going to do is I will stop over here because we have run out of time for today's class. You can of course go ahead and just complete this. In addition to that, we have some questions in the tutorial that also deal a little bit further with some examples of this sort. It is well worth doing that. The thing that you need to keep in mind is simply this. What is it that you are finally trying to do? You have come up with a proposed architecture which has one adder, one multiplier in this case. You have found out the scheduling time instants, the folding sets. They have been given to you right now, right? You don't know how to find them, but they have been given to you. Once they are given to you, you can then go ahead and calculate all the DF values. And once you have the DF values, you can then just basically say, okay, at time instant 1, the adder was supposed to execute this particular operation, A2. Where did it get its inputs from? From A1 and A4. A1 and A4 are both outputs of the adder. What are the DF values for that? For A1 it is 1, therefore put 1 register and take the output. For A4 it is 0, so directly take the output of this pipelined adder and feed it back to time instant 1. Okay, so in this way you can systematically construct it. You can put in the rest of these arcs as well and create what the final architecture should look like. Okay, so we'll look at this a little bit further in the next class. Like I said, couple of things. One is we don't have class tomorrow. Second is on Monday we will have a discussion of the tutorial problems. Okay, but in that case I want you to basically come prepared, meaning that I hope that everyone would have gone through the tutorial questions and raise the main problems that you are having, the parts that are difficult to understand, because I am not going to go through each and every one of the problems in detail step by step, but if you can point out any specific issues that you are facing, those can be addressed in class. Okay, all right, that's it.